I'm Anil Kumar. Welcome to my series on transformations. We'll discuss stretch factor and invariant lines in this particular video. Let me thank all the viewers and subscribers for watching my videos and posting excellent questions. Well, this video, especially for my new subscriber Deepthi, who has been sharing some questions and who wants to understand the concept of these transformations. So we'll discuss at length what is a stretch, what is a stretch factor, what are these invariant lines. With the help of many examples, figure for some of them is shown here. We'll also find out how to find the invariant line for the given condition. Sometimes the invariant lines are the coordinate axis. Well, at times we may have a negative stretch factor. In that case, the invariant lines are in between the two objects, the pre-image and the image which you get after transformations, right? So that means there are many types of different invariant lines, and therefore we may have to perform some intricate calculations to figure it out. But with my video, you will understand how easy it is to find really the invariant lines with just inspection and very simple steps. We'll actually solve test questions in this particular video to help you understand all the concepts required. In case you want to learn from me, you can always send me an email on the address given here. So let's begin with an illustrative example. So I'll take two particular cases. So here in the illustrative example, we're trying to understand what is a stretch factor and also what are invariant lines. So the concept of stretch, stretch factor, scale factor, and the invariant lines will be absolutely clear with this opening screen. Now what we have here is we have two examples going on. Let's take example one. Let's say let this be A for example. So here we have shown two triangles. The solid green one is the original triangle, and then a bigger one here is the transform triangle, which seems to be stretched, right? So that green triangle, if you compare with the other one, we have labeled them as triangle ABC and A dash, B dash, C dash, correct? So if you compare, what do you notice? You notice that the sides AB and AB dash, A dash, B dash are exactly same. So that means these lengths, which are their base, right? They are same. The horizontal sides are exactly same. However, the vertical sides, which are AC dash, the image, is twice the original side of AC. So what I'm trying to say here is that this particular length in the original triangle green is of 2 units. However, in the transform triangle, the blue one, it is 4 units. So this length here is from 2 to 6 in the graph, right? So that is 4 units. So basically, we see that there is a stretch factor of 2, right? It seems that this length has been stretched vertically by a factor of 2, right? So here what we notice is a vertical stretch by a factor of 2, right? So that is what we see. So I've written here vertical stretch by a factor. We are saying 2 is to 1. So basically, whenever you compare these sides, you see the ratio of image, which is A dash B dash, over the ratio of the original, which is AB. Now in this case, AB and A dash B dash is exactly 1, right? This is equal to 1. However, the ratio of A dash C dash over AC is basically equal to 4 over 2, which you could also write as 2 over 1. So that is a vertical stretch. Horizontally, it is not getting stretched. So these are special transformations where we are trying to figure out a reference line from where this stretch can be calculated. And this reference line is referred to as an invariant line, correct? So how do we figure this out? Now, in this particular case, we say that the ratio is 4 is to 2, or which could also write this as 2 is to 1, correct? So the ratio of 4 is to 2 is same as 2 is to 1. Now in this particular diagram, you can see that if I move from the horizontal line, which is for the um, original one step down, right? One step down. In that case, you have to go 2 steps down from the image, right? So in that case, we come to the same line. So one step down gets you to the x-axis from the original green triangle, and 2 steps down gets you to the x-axis once again, right? That means the x-axis could be a reference, right? So x-axis could be a reference. So if you see from the x-axis, which is y equals to 0, we find that the mapped points on the image are twice as far as they are on the original or the pre-image object, the triangle in this case. So the line y equals to 0, or the x-axis in this case, is treated as the invariant line. Do you get this point? So invariant line basically is the reference from where the vertical distance in this case can be compared, and that will be equal to the stretch factor, right? So that is what it is. So what we notice here is that both pre-image and the image are on the same side of the invariant line. So this is the invariant line for us, the x-axis, and from here we see that the origin is 1 unit away and the image is 2 units. They are in the ratio of 1 is to 2. Every point is in the ratio of x to 2x, right? So the ratio is maintained. So the vertical distance ratio we're talking about, and therefore the horizontal line, which is perpendicular to the vertical distance, is the invariant line, from where we could compare this particular ratio, which is 2 is to 1 in this particular case. So I hope you got this concept. Now, in the other example, what we notice here is that we have a pre-image which is green colored triangle ABC here, whose transformed image is shown in blue. But this time we have seen two operations. One is a reflection. It is reflected, correct? And it is also stretched. So when reflected, we will say that the stretch factor is negative because it is being reflected, correct? So whenever it gets reflected, we'll always consider the stretch factor as negative. Now, in this particular case, you notice that the length AC, the vertical length, has been stretched. Now, the ratio is again 2 is to 1, since the length of the image is 4 units vertically and that of the object pre-image is 2 units. So the comparison 4 over 2 again gives you 2 over 1. Since there is a reflection, right, it is considered to be negative. You understand? So it is negative 2 for the stretch factor. So that is the stretch factor. So basically, the mapping is such in this transformation that the y values which were at, let us say, a, then in the transformed image, the y value will be minus 2a, correct? So that is the kind of transformation which is taking place. So xy point in this particular case is getting transformed to x times minus 2y. You get the idea, because there is a reflection. In the previous case, it was on the same side and therefore it was 2y, right? So the transformation in the first case was from xy to x2y. You get the idea. So that was the kind of transformation in the previous case. Now these transformations are from a reference line, right? They're not always from the x-axis. Remember that part, right? So that is important to understand. Now, how do we find the invariant line? Now, since the stretch factor is minus 2, we're looking for a line in between the preimage and the image object. So from in between, one side, one direction will consider positive, the other as the negative, right? So it seems that the x-axis in this case also is the invariant line, since we have to go up 1 unit to get to the original triangle ABC, and then negative 2 times is the base of the reflected one or the image trans. You get the idea, right? So that is how we can get the invariant line. So in this case, the invariant line for us is again the x-axis, y equals to 0. So I hope you have understood the concept, and that is to find the stretch factor, we are comparing the changed value, whether it was changing in x or direction or in y direction, right? At present, we are considering only these two directions. So we find that it was same in the change in x, right? That was same. However, change in y is there, so it is vertically stretched, correct? So that is how we get the stretch factor. And if there is a reflection involved, then the invariant line is in between the object and the reflected image. If there is no reflection, then invariant line is on one side of both the object and its image, right? Now with that, let's take up some examples, rather define some terms first and then take up examples to understand them in better details. So what you learned here is that stretch is defined in terms of constant stretch factor and also a reference which is always invariant line. Now, invariant line is in the same direction, which is the direction of the side, which is not changing. So, the invariant line is like a reference for the measurement of the stretch, since the stretch is measured perpendicular to the invariant line. Now, a stretch is a linear transformation which enlarges all distances in a particular direction, perpendicular to the invariant line by a constant scale factor k. Now, enlarges is a general term which has been used, but the value of k, if it is greater than 0, then really it is stretch, right? Rather, I should say k greater than 1, right? So if k value is greater than 1, then it is a stretch. But if the k value is between 0 and 1, it is a compression. But still, we just call or treat this as a stretch, right? It is really a compression. We will treat this as a stretch factor by, let's say, 1 over k in that case, right? Okay, and another thing which we learned is that k value could be negative, and therefore it is customary to write this as an absolute value of k, right? So the positive value of k, if it is greater than 1, then truly it is a stretch. But if it is between 1 and 0, in that case it is a compression. Now, how do we find the scale factor? To find the scale factor, we need to just find the ratio of the shortest distance of the image point from the invariant line to the shortest distance of the original point from the invariant line. So that gives you the scale factor. Now, indirectly, you can actually just measure the maximum change, right? So you could also measure the change ratio. For example, in the last case, we did see how much one side is increased, right? The length of one side as compared to the length of the other side. That will also help us to get the scale factor. Now, scale factor is negative if reflection is involved, right? As in our example number 2, you saw that this is scale factor negative, and the first example, it was positive. If the scale factor is negative, then the stretches on the opposite sides, and that means that the invariant line must be in between the two objects. the pre-image and the image. For positive stretch factors, the image and the pre-image are on the same side of the invariant line, correct? Now, at times, as I said, x-axis could be an invariant line, not always. So we'll take up some examples where axis is an invariant line, and we'll also take up examples where the axis is not an invariant line. So here, you need to describe fully the transformation from the triangle ABC onto the triangle A dash, B dash, C dash. So ABC is the triangle in green. So this triangle given in green is triangle ABC. Now here you will notice that length AB is matching with the length A dash, B dash, C dash. That means that horizontally it is not stretching, it is exactly same. So it is not changing, it is invariant, right? So horizontally it is not changing, correct? But vertically it is changing. So vertically this length here is from 1 to 2, which is 1 unit. On the other hand, this length here is 1 to 3 units, right? So we can say that B dash C dash over BC is basically in the ratio of 3 is to 1. Now that 3 is to 1 gives you the scale factor. Do you see that? So this gives you the scale factor. So that is the first part. How do we find the scale factor, which is same as the stretch factor? So we just compare the distances. Now it is important that BC is 1 and B dash C dash is 3, and therefore the stretch factor is 3. So we can also say here scale factor is same as the stretch factor, right? So we say stretch factor equals to 3, correct? Or you can say 3 over 1. So that is what the stretch factor is. So we have found the solution for the first one. Now, how do we find invariant line? So the stretch factor, as you see, also written as 3 is to 1, is we're looking for a line from where the perpendicular distance is in the ratio of 3 is to 1. This is what we're looking for. Now, in this particular case, you can see that if I go 3 units down from here, then where do I reach? I reach the x-axis. Similarly, if I go 1 unit down from the base of the original, then also I reach what? I reach the x-axis. So for both we reach the x-axis. Therefore, this x-axis will be treated as invariant line. Now this way, it is very easy to find the invariant line itself. So we related the stretch factor, right? So we related the stretch factor with perpendicular distance. And once you do that, what you get is the invariant line, right? So that gives you invariant line. Do you see that? So that is the best way of finding the equation of invariant line. So once you land up there, you know that the invariant line has to be x-axis, which is y equals to 0. Is that clear to you? Right? So in this case, the invariant line must be the horizontal line as the stretch is vertical, right? Not the horizontal. Since the stretch is vertical, invariant line must be a horizontal line. Now the ratio of distances from the invariant line to the image point and the original point is 3 is to 1, and therefore x-axis, which is y equals to 0, is the invariant line. So I hope you got the concept, correct? We'll apply this concept once again to really consolidate our learnings. Now in this case, what you notice is that the vertical distances of the two triangles are same, correct? So we have exactly a similar question. You need to describe the transformation from the triangle ABC onto the triangle A dash, B dash, C dash. And then you need to determine the stretch factor and the invariant line. So what are you going to do? Well, just compare the, the side lengths, right? Now each side length you need to compare clearly. What we notice here is that the vertical side lengths are same, right? So we have no vertical stretch since those are the same. However, the horizontal sides are different. We have 2 units here, and for the other one, we have how many units, right? 2, 4, and 6. Now these are 6 units. So in this case, we find that the ratio of A dash B dash over AB is basically equals to 6 over 2, which can be written as 3 over 1. So that is the ratio. Now this ratio is in the direction of horizontal direction, and therefore we know that the invariant line will be vertical, correct? So we have a vertical invariant line. Is that clear to you? Now how do we find how far is the invariant line? Well, the ratio in this case is 3 is to 1. So what we're looking for is where could be a point which is 3 units from this. So we can go 3 units down. And when you go 3 units down, where do you land up? You land up on the y-axis. And 1 unit down from the original, you land up again on the y-axis. And therefore, the invariant line is, in this case, the y-axis. Do you see that? The perpendicular distance of the points on the object and the points on the image are in the ratio of 3 is to 1 from the y-axis, and therefore that becomes the invariant line. So I hope you got the concept, right? So I like you to again go through this, try to understand what we're trying to see here, and then move forward. Now, in the next example, what you notice is that the shape is exactly similar, right? That is kind of similar. How? What you see is a different orientation. So we notice that there is a reflection, right? So in this case, we have a reflection. The orientation changes, right? Now, whenever that is the case, we have a negative factor to be incorporated into the stretch. So that is kind of important. And second, we also expect the invariant line this time to be in between the two objects, correct? So that is kind of important. So with this example, we'll understand how to take care of negative scale factors. The question again is describe fully the transformation from the triangle ABC onto A dash B dash C dash, determine the stretch factor and the invariant line. Now that's the diagram given to you. What do you notice? Well, from the orientation of the image, we can see that the stretch factor is negative. And so the invariant line will be in between the two. Let's compare the distances, right? The horizontal distance, which in this case is AB to A dash B dash, right? So we'll write normally the image up, right? And denominator is the original. In this case, the image is how much? It is from 2 to minus 2 to minus 6, which in this case is 4, and AB is 2. So we have a ratio of 2 is to 1 in this particular case. So that is the change horizontally. The vertically, both sides are equal. Now, since it is a horizontal change, we know that the invariant line will be vertical, correct? So, in this case, we have a vertical line which is the invariant line for us. Now, which vertical line? 2 is to 1 is the ratio. So, from here, we can go 2 units and from there 1 unit. That is how we could find it. Now also note that since there is a reflection, right? Since there is a reflection, this change will be qualified with a negative sign. So truly speaking, the ratio is minus 2 to 1. Correct? Makes sense. So you actually go from the invariant line, which is y-axis in this case, so that becomes the invariant line x equals to 0. So you go 1 unit towards the main original figure, the pre-image, and minus 2 towards the image. So that gives you minus 2 is to 1 ratio. You get the idea. So the steps involved are check which side is being stretched. In this case, a horizontal side is stretched. Since only horizontal side is being stretched, vertical line is going to be the invariant line. A vertical line which actually divides the distance, horizontal distance, in the ratio of stretch factor is the solution. So how do we do it? We actually go towards the center from the two non-changing sides in the ratio of the stretch factor, right? In this case, minus 2, 1. So we are going right minus 2 and 1 from the original left, and both meet at one line, which is the y-axis. Therefore, y-axis is the invariant line. Is that clear to you? That is how we're finding it. So I hope that is absolutely clear. Now, let's take another example. Here it is a very interesting example in which we have a common base. You can see in the figure that the two triangles, the original solid green and the other one blue, which is the stretched transformed triangle. So in this case also, you need to describe the transformation from the triangle ABC to A dash B dash C dash. And then you need to determine the stretch factor and the equation of the invariant line. So let's begin with this. We have the common base, so no change in the base, which is horizontal distance. However, vertically there is a change. The ratio A dash B dash, or rather I should say C dash, since it is vertical, I've made C is that point. So A dash C dash over AC in this particular case, this ratio is 4 is to 2 or 2 is to 1, right? That is the ratio. Now, we have the stretch factor of 2 in this particular case. So that is a part of our answer. So we do have a stretch factor which is of 2. Now, how do we find the invariant line? Well, from the base or from any point on this triangle, the distance should be in the ratio of 2 is to 1, right? So if I move 2 units from the one of these lines, in that case, what happens? So in this particular scene, since we have a common base, since we have a common base, you can compare from the base itself. If you move 1 unit, rather 2 units, to reach the top of the original triangle, and to reach the top of the other triangle, you have to go twice, which is 4 times 4, right? So that compares with the stretch factor, and therefore we now know that the invariant line is y equals to 2. Now, whenever we have a case with common base, that common base is the equation of invariant line. Clear? So the common base, let me write down, represents invariant line. Is that clear to write? So in this case, it is y equals to 2. So that is how you get the invariant line, right? Now here is another example in which we have two triangles. The solid green one is ABC pre-image. The image of transformed triangle is A dash B dash C dash, which is the blue triangle not filled in. You need to find once again the stretch factor and the equation of invariant line. So you can actually pause at this stage, write down your answer, and then look into my suggestions. Now let's look into the stretch factor, which is A dash C dash over AC. Since the vertical sides are changing, right? There is a change in vertical side. So A dash C dash is this particular length, which is from 2 to 6, which is 4, 1, 2, 3, 4 units. However, the original is only 2 units. Therefore, the stretch factor is 4 over 2 or 2 over 1, right? That is the stretch factor. Now, to find the equation of the invariant line, what can you do? They do not have the common base, so what we'll do here is, from the actual drawing, we'll go 1 unit down, right? So we want to find the inference, and then from here, we go 2 units down, right? So if you go from here 1 and 1, 2 units down, then where do you reach? Well, in this particular case, you do not get to the same point. You see, 2 units down, you reach only this point, correct? So it doesn't really work in this particular fashion. However, if we go for the ratio of 2 units, right, 4 is to 2 is also the ratio. Since we did not reach to a common line, what we can now do is we can try 2 units. So if I go 2 units down, then from here, do we reach at the same place by going down 4 units? Yes, we do. And therefore, the line which is y equals to minus 2 becomes the invariant line. Do you see? There has to be a common factor. So, invariant line basically is the one which is a reference line which matches with the vertical distance of the scale factor. Correct? So, note here that whenever you try to find the invariant line, so invariant line provides reference for vertical distance. In this case, I can write in general for distance ratio. Perpendicular distance ratio to be same as stretch factor. Clear? So the stretch factor was 4 is to 2, and we found a line which is y equals to 2 from where it is 2 units to the original pre-image and 4 units to the image, and that is how you get the invariant point. I hope that is clear, right? Let's take up more examination questions. Now here in this particular case, you can see the two triangles. The question again is describe fully the transformation from the triangle ABC to triangle A dash B dash C dash. Determine the stretch factor and the invariant line. So clearly what you notice that the vertical distances are same, right? However, the horizontal distances are not same. So in this case, you can find that the ratio A dash B dash over AB is 1, is how much? It is, well, this is A dash B dash is 1 over 2, right? So this is 1 unit and that is 2 units, 1 over 2. So the ratio is half, and therefore we are looking for something invariant line in between, since there is also a reflection, right? Change in orientation, and therefore effectively the scale factor, I should say, will be what? It is P negative, right? So it'll be 1 is to negative 2, right? So that is how we are going to see the scale factor, right? Now in this particular case, 1 is to negative 2 is the scale factor. That means the line is somewhere in between. Now in this case, if you see the distance B to B dash, this is 3 units. So in between 1 unit, let me draw the line. So what we notice here is that the distance is now from point B 1 unit, right? And the other one is 2 units. And therefore, we get our line of invariant line whose equation is x equals to 5, from where it matches, the distance matches the scale factor, and therefore that becomes the invariant line. So what we did was that since there is a reflection, we know we have a negative scale factor. That means invariant line should be in between the pre-image and the image, and the distance of the constant lines, you can say, are in the same ratio, and that will figure out the every point in this object should be same ratio for that matter. And we just check point B and B dash. You could do A and A dash also. So this also is in the same ratio of 1 is to 2. So from here, going to A is 2 and going to A dash is 2 and to A is minus 4. and that is the scale factor 1 is to minus 2, or which is also same as 2 is to minus 4, right? So either one of them. So that is how the images are being matched. So I hope with this the concept of finding the stretch factor and the equation of the invariant line is absolutely clear. Feel free to write your comment, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.